So there are methods. One of the methods that is used in order to analyze a statically indeterminate beam without yielding of support is the moment distribution method. So let me just discuss the analysis for statically indeterminate beams without yielding of support. So there are methods. One of the methods that is used in order to analyze a statically indeterminate beam without yielding of support is the moment distribution method. So let me first discuss with you the moment distribution methods. So we have a method of successive approximation. This one was popularized by Hardy Cross in 1932. So what the moment distribution method is done is you can carry out any degree of accuracy depending upon the number of corrections. And in the moment distribution method, actually there are four concepts which we are going to use in the structural mechanics for the analysis of beam using the moment distribution method. One is the FEM. The other one is the rotational stiffness of the member. Then you have the internal stiffness of the member and the carryover moment factor. Okay. So the fixed end moment at each end of the member is determined. So for any kind of load supported by a beam fixed at both ends, it will induce a fixed end moment at each of the beam. Okay, so that means this is a kind of statically indeterminate beam. So that's the reason why we need to make use of another method, which is the moment distribution method. So the moment distribution method is a method of approximation. Okay? So kung meron tayo ditong loads, okay, lateral forces, ang effect niyan sa column is definitely horizontal din. So that's why meron tayo ditong mga figure here to show yung elastic curve na mangyayari kapag meron tayong ginamit na moment distribution method. Okay? So if you are going to take a look at that, that's how we use the moment distribution method. So the clockwise positive, counterclockwise negative. So that means this is a negative moment while this one is a positive moment. And the second property that we need to take note of is the rotational stiffness. Okay, so when we talk about rotational stiffness, it is about beam stiffness. It is the moment required at the simply supported end of a beam in order to produce unit rotation at the end, and the other end is a rigidly fixed end. That means there is no relative linear displacement of two ends of the beam. So considering the rotational stiffness, okay, if you have a cantilever beam such as this one, can you still view what I am writing?
Yes po, ma'am.
Okay. So kung meron tayong cantilever beam such as this one, yung rotational stiffness na tinatawag natin, okay. So kung lalagay tayo dito ng tangent line, so meron siyang angle. Okay? And then, of course, kung meron kang load dito, definitely ang deflection, di ba? Remember, ang deflection ay maximum deflection nasa free end kapag ka-cantilever. So, meron kang moment here, okay? And you also have a moment here. Okay? And of course, you have the reaction here at point A. So if you are going to determine the rotational stiffness, you go back to our deviation, yung formula natin ng deviation, di ba? Deviation is a tangent drawn at A to point B is equals to, ano nga ulit? Galing dun sa ating previous na discussion. How do you determine the deviation? If you have a tangent drawn at A to point B, how do you determine the deviation? The deviation from tangent drawn at A to point B is simply equals to 1 over EI multiplied by the area of the moment diagram from A to B multiplied by bar X from point B, wherein bar X is the centroidal distance of point B. Okay? So, yun yung theta na tinatawag natin or rotational stiffness. And in the case of cantilever beam, usually yung moment sa A is equals to 1/2 of the moment dito sa B. Okay? 1/2 negative moment. So, moment at A is equals to negative 1/2 moment at B. Okay? You have the beam stiffness, K. Okay, beam stiffness. Okay. You also have the absolute K. Okay. Dalawa yung klase ng stiffness. One is beam stiffness, the other one is absolute K. So the absolute K is simply equals to 4 EI all over L, wherein E is the modulus of elasticity, I is the moment of inertia, and L is the span length. So for most structure, the value of the modulus of elasticity is the same for all members. And then you have the beam stiffness. Aside from the absolute stiffness, we also have the relative stiffness. So the relative stiffness is equals to I over L. Okay, wherein I is the moment of inertia and L is the span length. Okay? Then aside from that, we have the modified stiffness factor. So the modified stiffness factor in cases when the far end is also hinged, the stiffness factor is 3/4 of the value when the far end is fixed. And then of course you have the stiffness factor of the near end when the far end is hinged in the is 3/4 of that of the far end is fixed. So you have 3/4. If this is the stiffness, 4 times EI, and then you multiply it by rotational stiffness theta over L, all you have to do is to multiply this by 3/4. Kung ang far end, the stiffness factor of the near end when the far end is hinged is 3/4 of that when the far end is fixed. Okay, so kung ang far end mo ay fixed, ang near end mo naman is hinged, then you can use the value of 3/4 multiplied by the value of relative absolute value of K for EI over L, and then you multiply this again by theta. Okay. Another property that we need to identify is the carryover moment or the COM. The COM or the carryover moment is the moment induced at the fixed end of a beam by the action of a moment applied at the other end. Okay, again, it is the moment induced at the fixed end of a beam by the action of a moment applied at the other end. So, how many properties na yung ating banggit? Fixed end moment, then relative stiffness, then carryover moment factor, or the modified stiffness factor also, and the rotational stiffness. So, you have the COM for the distribution. And then, of course, you have to determine the relative stiffness. And then you have the distribution factor. The distribution factor is is equals to K over summation of KI, wherein K is the number of member in question. K of the member in question. So, ibig sabihin, yung beam stiffness of the member in section. So, if you would like to determine the distribution factor, that is simply equals to K over summation of K for that particular element. So, lateral stiffness is a measure of resistance to lateral displacement of one end of a member when both of its ends are fixed against rotation. So, ito yung displacement. So, yung lateral displacement is caused by the lateral load. So, for the lateral stiffness, if we are going to have the lateral stiffness, and the last one is the carryover factor. Okay, for the carryover factor, we have the COF. This is the last, okay? So this is the last property that you need to identify. The carryover factor, if both ends of a member are unyielding supports, then the carryover factor is the ratio of the moment at the fixed end to the moment producing rotation at the other end. Again,